Yes,
Great.
good.
So I'm Pin-Gao from HIA. So first of all, I would like to thank the organizers of the STEAM conference for the invitation. And the topic I'm going to talk about today is the atmospherical tides on a hot Jupiter. So from background picture, you can see which is actually an artist's impression showing a gas giant planet, which is very close to the its host star. The typical period is a few days, and this is a hot Jupiter. So as you may know, the hot Jupiter is the first class of exoplanets that were detected around the solar type star. Because for that reason, the half of the Nobel Prize in Physics 2019 was awarded to Michel Mayor and the Didier Queloz for their discovery, of course, for their outstanding contribution in the field. So basically there are two major detection methods. First one is radial velocity. So when there's an unseen planet orbiting its parent star, so the parent star is wobbling, and therefore the absorption life on the parent star is blue shift and the red shift depends on location of planet, which can be detected by the observers. In the transit method, so you can see this. There's a dip in the transit light curve as the planet moving in front of the star if this orbit is almost edge on. So from this radial velocity, people can take the information of the mass of the planet, and on the other hand, the radius information of the planet can be extracted from the transit method. So put together, people can get this the bulk density of the planet, which can be possibly used to infer the composition of the planet. So now let me just briefly introduce the concept of atmospherical or thermal tides. Because we are talking about the hot Jupiter, they are very close to their parent star. So the tidal interaction is expected to be very important. So as you all know, the gravitational tides are driven by the differential gravity on different parts of the celestial body. So similarly, the atmospheric can be driven by differential stellar heating on different parts of the celestial body. So what I'm going to explain to you is the atmospherical tides can produce the global circulation and the thermal bulge. So let's move to the first subject, global circulation. So here is a phase curve of a hot Jupiter HD 189763b. So the data were taken with the Spitzer telescope at the wavelength 3.6 micron. So dashed line is plotted against the bottom of the second ellipse during for the entire transit light curve. So all the flux below this dashed line comes from the stellar irradiation. And everything else above this line comes from the thermal emission from the planet. So it's not a surprise to see the modulation. You see this modulation of the light curve due to the thermal emission from the planet, because at different orbital phase, you have different portion of the day side and night side coming to your view. But what is intriguing is this maximum flux from the thermal emission from the planet actually occurs about several hours before the second eclipse. So if we assume the planet is so close to its parent star, so it's already tidally locked, then in this peak, the maximum thermal emission actually should peak at the moment of the second eclipse, but it's not the case. So the person who did an observation and proposed in this paper this there's an equatorial rotating flow which carries the heat, stellar heat, which originally concentrated on substellar point, and this was brought by this global scale super rotating flow to somewhere downstream. So they produce this offset between these the location of maximum flux and the substellar point. So so although the concept of equatorial superrotation was already predicted a long time ago in a GCN simulation by Schulman and Gill, but what actually happened, how this transfer angle is transferred toward the equator actually was unknown at that time. So one way of doing this is a wave, which can carry angular momentum and redistribute angular momentum from one part of the planet to another part. So Google and Ogilvy actually probably among the first people carry out this linear analysis. They show these large-scale equatorial waves, which is driven by the intense stellar irradiation, and then can transfer angular momentum in a hot Jupiter atmosphere. So as shown in the plot, the vertical axis is the torque, and the x-axis is the optical depth of the atmosphere. So you can see this, the wave actually bring angular momentum from the bottom of the atmosphere to the upper part of the atmosphere, therefore to spin up the atmosphere, upper part of the atmosphere. Of course, in this scenario, there's only this angular momentum transfer in the radial direction in the atmosphere, and it's not clear how the angular momentum can be transferred to the equator. It was not really realized until Schulman and Pavani in 2010. They published a paper, and they demonstrated even for tightly locked atmosphere, you start with this atmosphere, and the stellar heating on the permanent day side can excite equatorial wave, which is some kind of wave related to the Coriolis force. And then it can accelerate equatorial gas along the spin direction. So what's going on is you see the star over here, this corresponds to the substellar point, and the stellar heating over here can drive over the streamline and the pressure pattern. The blue line corresponds, the blue curve corresponds to the low pressure region. The red color corresponds to the high pressure. So actually, it can be shown this from this complicated weather pattern, which can be decomposed into two simple modes. One is the equatorial Kelvin mode, the other is the equatorial Rossby mode. So the streamline from this combination of the two modes can transfer angular momentum from the polar region to the equator, so therefore leading to the super rotating flow. So later on, Xiaomi Cai, Ian Dixon, and myself extended this seminar work to the 3D cases, and then we confirmed the results. So let's move on to the next topic, the thermology excited by thermotypes. The motivation of this is most of the hot Jupiter are actually too big to be explained by the current theoretical model. So just imagine there's a gigantic water tank. It turns out most of the hot Jupiter are just density is too low, and they are floating in the water. By contrast, the Jupiter is kind of more compact, so the density is high, so it sinks to the bottom. So the bottom line is all the hot Jupiter are actually bigger than our Jupiter in the solar system. So in particular, somehow this so-called the radius anomaly, it's the large radii of the hot Jupiter, has something to do with this incident flux from the host stars. So the picture on the left shows this clear positive trend between the planet radius and the incident flux received by the planet. On the other hand, the picture on the right shows these the result from the 4 different transit surveys, which gives this the planet radius. The red color are these the planet with smaller radii, and the blue color is the planet with the large radii. And then this blue color actually close to this stellar isochron, which is about 13 giga years old. It's quite old for Massive star. On the other hand, is the red color, actually close to the isochrone, correspond to only about 200 million years. So in principle, you can see the data, the transit data from different surveys anomalously indicate it's when the hot Jupiter seem to be becomes larger and larger as their host star age and becomes more luminous. So of course, that's just hint there's a correlation between the incident flux received by planet and the planet radius. So this phenomenon is called hot Jupiter reinflation. So there's a couple models available in the market, but today I'm just focused on one particular model related to atmospherical tides. So the model by itself can be illustrated by this simple picture. So basically, there's a gravitational tide everybody are familiar with. That's a gravitational bulge indicated by this blue color, excited by the stellar gravitational field. But if the stellar irradiation is strong enough, that can excite another bulge, in principle, indicated by this red color. And if the so-called thermal bulge, if the thermal bulge is pointing in different direction, in this case in the opposite direction to this direction to the gravitational bulge with respect to this dashed line toward the central star, so that's likely to for the stellar gravity field to exert the opposite different sign of the torque on these two different the bulge, and therefore the total torque can be canceled out. In other words, hot Jupiter is ended with in a stage of the synchronous rotation, and therefore there's a continuous supply of the tidal heating to make the planet bigger. So Aris and Socrates worked out the detail and computed the quadrupole moment Q22 as a function of the forcing period, which is related to this orbital frequency and the spin frequency. So in this particular model, because of the presence of the thermal bulge, the planet is actually not tidally locked. So you can see they show that the strength of the quadrupole moment associated with the thermal bulge peaked at about 2 days, which correspond to GMO oscillations excited by irradiation. So they show actually argue the strength of a quadrupole moment for this thermal tide is strong enough to counteract this torque on the gravitational tide. So somehow the model can work. But this seminar work is pretty good. It's already pretty good, but they didn't take into account this any radiative damping on the waves. So later on, toward more realistic atmospheric ray model, it's a French group, Lacombe and the heat collaborator, include this Newtonian cooling. Newtonian cooling is just some kind of a damping process, radial damping process, controlled by this thermal time scale, cooling time scale, which is typical for the heating layer of a stellar irradiation in the hot Jupiter atmosphere is typically about 0.1 to 1 days. So take that into account and they show actually the strength of the thermal bulge, the quadrupole moment actually is dramatically dropped by 1 or 2 magnitude as you can see compared to this original curve in blue. So that just implies this model actually cannot work in the sense it's too weak to put the thermal bulge is just too weak to counteract this the torque on this gravitational bulge. So in the meanwhile, almost at the same time, and I was thinking about different model, the so-called twostring approximation for more realistic atmospherical model. So in this framework, there's 2 strings. So the one string is referred to the incoming stellar irradiation. Most of this light is at this visible wavelengths, which is absorbed in the atmosphere controlled by this visible opacity kappa V. And the other string is referred to the outgoing thermal radiation. Most of these lies actually at the near infrared wavelengths, which consists of internal radiation, and most importantly, including reprocessing incoming state irradiation characterized by the thermal opacity, thermal kappa over here. So the whole this radio transfer in the atmosphere is controlled by the two opacity. So in collaboration with Pin and Yan, we constructed a model for the atmosphere, this so-called double gray atmosphere, because there's two opacities. So as shown by these two figures, indicated by the temperature profile as function of the height. The height is indicated by the pressure. So it turns out the atmospheric structure or temperature profile depends on this competition between these two opacity. When this kappa V is smaller than kappa thermal, so the incident flux can penetrate deeper into the atmosphere and then reprocess and it becomes near infrared, and then it's trapped in there and produces this bump, temperature bump, just because due to this greenhouse effect. By contrast, when kappa V is bigger than kappa thermal, because right now the visible opacity is large, so most of the incident flux actually absorbed in the upper atmosphere, so that's therefore producing this temperature inversion in the atmosphere. So with this temperature profile as a background, so we are able to carry out this linear perturbation theory to investigate whether how these thermotypes responds to the stellar irradiation in order to produce the thermal bulge. The most important term is in the energy equation, which is the entropy gradient, including two terms. The first term is the heat term, which excites these semi-diurnal thermotidal waves. The second term is a term associated with the radiative perturbation. So in the work by in the French group, they model this as Newtonian damping, Newtonian cooling, which is proportional to the temperature perturbation. But the efficiency of this damping is controlled by this cooling time scale. In our work, based on twostring approximation, so we can recover this term. It's a term similar to the Newtonian cooling, but there's an additional term associated with absorption of this thermal irradiation that just due to the greenhouse effect. So therefore, we perform the calculation of this crucible moment of the thermal bulge using the Newtonian damping model by this French group, as indicated by this green line, in comparison with our result, which incorporate the greenhouse effect. So as you can see, this the crucible moment associated with the thermal bulge with the greenhouse is much bigger than this, stronger than this the crucible moment without this greenhouse effect. So the take-home message from our work is the greenhouse effect can be substantial against radiative cooling, and therefore leading to almost undamped thermal tidal bulge. So the question right now is how to do the reality check. So there are several, of course, there are several ways to do this. But today I'm just bringing over the issue which has been intensely discussed recently by several people. They published a few papers. They explore the possibility whether this one Jupiter reinflation actually can occur around the post-main sequence stars. So what does that mean is this, as the star evolved from main sequence, so the star becomes more luminous, and even the warm Jupiter, which is located far away compared to from their host star compared to the hot Jupiters, can receive a tremendous amount of luminosity from the star, and therefore can be also reinflated. So far, there's two or three candidates already from the observation and showing us some kind of evidence for warm Jupiter inflation. So if this is really true, then our model based on this tidal thermotypes cannot work because warm Jupiters are far enough from the whole stars to be tidally important. So in other words, other model will then be favored. So I didn't have time to talk about other models, but the audience can refer to these two papers or the papers above to understand other models. So it's worth mentioning, TESS is successor of the Kepler Space Telescope. Will observe about 400,000 evolved stars, which will give a big sample of this sample of the data, and which can be used to justify whether warm Jupiter inflation can really occur around evolved stars. So finally, I want to touch upon this something to do with the composition of the hot Jupiter atmosphere, because when I talk about greenhouse effect, then certainly this should depend on the opacity, and it should depends on this composition. And the composition in the atmosphere can be, in principle, probed by this transit spectroscopy. So just here, just show this one of the example for hot Jupiter was 121b. So what are shown here is just emission spectra, which are basically fitted to the data from HST and speeder. And so the corresponding temperature profile and the abundance of molecules which responsible for this opacity are shown here in this figure. So from this work, they show that two models actually work very well to fit the data well. So these two models, the first one is based on this carbon to oxygen ratio is equal to the solar abundance 0.5. The other one is a little bit over solar abundance C2O ratio is equal to 1. So far with this data, these two models cannot be distinguished. However, in the future, when JWST, that is James Webb Space Telescope coming online, so there will be more accurate data and then to better constrain the C2O ratio. And then this ratio actually is not only important for our model, but also can be connected to this planet formation. So it's widely believed the hot Jupiter is not formed in situ, but it's formed far away from the central star in the proplanetary disk. So this figure shows the CO2O ratio in the proplanetary disk, in the gas phase, or in a gas phase, or in the dust phase, as a function of the distance away from the central star. So because carbon and oxygen have different condensation temperature throughout the disk, so that will give you different C2O ratio at different location throughout the disk, shown by this blue curve. So the idea is this: if you consider gas giant planet forming inside this gaseous disk, creating the surrounding gas, and if the planet form here and there, so the C2O ratio in the atmosphere of the planet is should be different. So maybe knowing this the C2O ratio in the hot Jupiter atmosphere can provide valuable information to shed light on where in the proplanetary disk the planet actually formed. So here comes the summary. The thermal tidal waves are responsible for equatorial superrotation, which is consistent with the phase curve of observations of most of the hot Jupiters. Thermal tidal waves may drive thermal biology to desynchronize the spin of a hot Jupiter and thus reinflate hot Jupiter, which can be further enhanced by the greenhouse effect. Hot Jupiter, whether influenced by greenhouse effect, may shed light on planet formation via the C2O ratio. So finally, our model may not be able to explain the warm Jupiter inflation if that's really there. around evolved star. So I will stop here. Thank you for listening.